Hello everyone, my name is Bogdan Mankiuk and this talk will be about augmenting the algebraic connectivity of graphs. This is joint work with Panpang and Hasun. The outline for the talk is as follows. I will begin by introducing the problem and present our main result. Then I will give an overview of our two main technical contributions, and finally I will end with some concluding remarks. So, at the very high level, the problem that we're interested in is improving the overall connectivity of a graph. Suppose in this example we have the graph G, and let's think of every node as a city and every edge as a road connecting two cities. What we're interested in is building more roads between the cities to improve the overall transition. And of course, one solution that you may think of is we can simply build a road between any pair of two cities, and of course that will improve the overall connectivity. However, that is a bit too idealistic and may be infeasible in practice due to various constraints. A more realistic approach is the following, where we're only allowed to build a road only between certain pairs of cities, and these roads are indicated by the gray edges in this example. And again, one solution to solve our connectivity problems is to essentially append all these gray edges to our graph. And while it is true that this improves the overall connectivity, there will be a lot of redundant edges added, which can incur a significant cost in practice. So what we really want is something more like this, where we add to our network only the edges that significantly improve the overall connectivity. In order to formalize the problem, I will introduce a sequence of definitions. So, given an undirected graph G on n vertices and non-negative edge weights W, the Laplacian matrix of G is an n by n matrix whose rows and columns are indexed by the vertices in V, and whose diagonal entries LUU is nothing but the degree of the vertex U, while the off-diagonal entries UV are just minus the weight UV. Here's an example of a graph and its associated Laplacian matrix. And by the definition of the Laplacian matrix, we see that LG is symmetric and real valued, which means that it has n real eigenvalues, which we'll call lambda 1 up to lambda n. And it is a known fact that the smallest eigenvalue, lambda 1, is always 0. However, more interesting is to consider the second eigenvalue, lambda 2, which is non-trivial in general, and this is exactly what's referred in the literature as the algebraic connectivity of G. And okay, at this point you may be thinking, why are we looking at lambda 2? What does this have to do with the overall connectivity of our graph? But it turns out that lambda 2 is a robust measure to study the connectivity of our graph G. In particular, the larger the value of lambda 2, the better connected our graph is. And intuitively, adding extra edges to G increases its algebraic connectivity. Motivated by our example, I'd like to draw your attention upon two questions that arise. The first one is, given a graph G and the candidate edge set EW, is it possible to increase its algebraic connectivity, or its overall connectivity, just by adding few edges F from EW? And the second question, if this is the case, if it is possible to improve its connectivity with only few edges, is there a way to efficiently find this edge set reasonably fast? And before going further, I would like to set some notation. So for the rest of this talk, I will refer to G to be the underlying base graph, the one for which we want to increase this algebraic connectivity. W will essentially denote the candidate edges, and M will be a parameter to denote the size of the candidate edges, while K is another parameter which is used to measure the size of the good set of edges, the set F. And now we are ready to introduce this notion of K-gamma augmentability. So we say that a graph G is K-gamma augmentable with respect to W if there exists a subset F of good edges from the candidate ones of size K and weights WF such that the resulting graph H, which is nothing but the previous graph G to which we've appended our set F, has algebraic connectivity at least gamma. So intuitively, you should see this definition as follows. If G happens to be K gamma augmentable with respect to W, by adding only K edges from W to G, we can boost its algebraic connectivity to be at least gamma. Our work positively answers the two questions that I've stated before, and here is an informal statement of our result. We showed that there exists an algorithm such that if G happens to be augmentable with respect to W, the algorithm will find this set F and the corresponding edge weights WF with the size of F to be order of K, and if G cannot be augmented from W, the algorithm will output null. Notice that for the parameter gamma, for the targeted algebraic connectivity, we have this delta times n to the minus epsilon, where delta is just the maximum degree of the graphs G and W, and epsilon is an arbitrarily small positive constant. Moreover, our algorithm runs in time O tilde mk squared n to the epsilon, and you may see that for small values of k, such that, for example, take k to be log n, the running time is almost linear. The best previous result known before our work for this problem of augmenting the algebraic connectivity was given by Kola et al. In 2010. They give an algorithm that runs in time mkn squared, which is significantly inferior to ours. However, their algorithm can be applied in a more general setting. Our algorithm is based on two technical components. In the first one, we show that the problem of augmenting the algebraic connectivity can be formulated as a semi-definite program, and we provide a fast solver for this program, which will essentially determine whether the graph G is augmentable with respect to W or not. And our second technical component is a fast algorithm for subgraph sparsification. I will talk more about this problem later on, but at this point, essentially this part, in the case when G is augmentable with respect to W, it will find this set F of good edges with size of F to be order of K. Okay, so far I have introduced the problem and I've given an overview about our result. Now I will focus on the first technical component, which is the fast SDP solver. As I said before, the problem of augmenting the algebraic connectivity can be expressed as a semi-definite program, which you see over here. We denote it as PRIMALSDP, and this is based on the work of Ghosh and Boyd in 2006. And the constraints of the semi-definite program are quite natural with respect to our problem. For example, combining the first two constraints, this will basically ensure that the resulting graph will have eigenvalues at least gamma times delta. Most of the other constraints are regarding the weight of the added edges. So, for example, the third constraint ensures that the total added edge weight is at most k. And the next two ones ensure that the added weight of the edges is a number between 0 and 1. A crucial observation about our semi-definite program is the following. If the graph G happens to be k gamma delta augmentable with respect to W, the SDP will have at least one feasible solution. So to see why this is the case, we know that if G is augmentable with respect to W, there exists this set F of k edges, such that if we append this set F to our graph G, we improve the algebraic connectivity to be at least gamma delta. And the claim is that from this set F, we can actually construct a feasible solution for our SDP. So we do this simply by setting WE to be 1 for all the edges in F and WE to be 0 for all the edges E that are not in F. And you see that by doing this, all the constraints regarding the edge weights are satisfied, while the second constraint that we have now essentially translates to adding the edges in F to G increases all the eigenvalues to be gamma times delta, all the non-trivial eigenvalues. And of course, this is the case because F is the set of the edges used to augment the graph G. So again, the main takeaway point from this slide is the following remark, which is if G happens to be augmentable with respect to W, the primal SDP is feasible. And here is our result regarding the SDP. We show that there is an algorithm running in time O tilde m plus n divided by gamma squared that either finds an approximate solution to the primal SDP or certifies that there is no feasible solution for the primal. Basically, the second point in here says that the algorithm can produce a certificate if the graph G is not augmentable with respect to W. And the proof idea is as follows. We first formalize the dual SDP from the primal SDP, and we applied the standard matrix multiplicative weights update algorithm to the primal and the dual, framework developed by Aurora and Kale in 2016. We formalized the dual, which you can see on the left-hand side here. I will not insist too much on it. I will just mention that this dual SDP is very similar to the semi-definite program for the balanced sparses cut problem, for which we know that we can solve the SDP fast, and this gives good indication that our dual SDP can also be solved fast. And another point to remark is that the constraints of this dual SDP are a bit more complicated in the sense that we have matrix, vector, and scalar constraints. And for the analysis purpose, we unify all of these constraints into a new block matrix. The framework for solving the SDP goes as follows. We start with X1, which is an embedding from candidate solution for our dual SDP. And we let the following process run iteratively for capital T rounds. In each round, small t, from an embedding x to the t, we pass it to some oracle, and the oracle will check if our embedding xt satisfies a certain constraint c of xt. If the constraint is satisfied, we show that from this xt we can construct a solution to the dual SDP program. And because we can construct a solution to the dual, this means that the primal will be infeasible. And if the primal is infeasible, we've already established that the graph cannot be augmentable. However, if the condition is not satisfied, by the output of the oracle, we can update our embedding xt efficiently to xt plus 1 and go to the next round. And the claim is that this process is guaranteed to terminate in a small number of iterations. You see why this is the case? As I said, we let the process run for capital T rounds. If in any round the output of the oracle is yes, we are essentially done, because that's the case when the graph G is not augmentable with respect to W. However, if all the rounds output no, we can use all the embeddings x1 up to x capital T to construct an approximate solution for our primal SDP. And to go from the embedding xt to xt plus 1, we use the matrix multiplicative weights update algorithm and fast dimensionality reduction. And of course, our main contribution is designing such an oracle and a particular constraint that xt is applied to. So completing this framework. Okay, now I will move on to our second main technical contribution, which is about the subgraph sparsification, and this is of independent interest to our problem. So remember, in here we consider graphs G, which are augmentable with respect to W, and the goal is to find a subset F of the edges of size order of k, such that when we add these edges to G, the overall algebraic connectivity lambda 2 of the resulting graph LH is similar to the algebraic connectivity of G plus W. And you should really view this as lambda 2 of LG plus W is in some sense the best lambda 2 we can hope for, because this corresponds to adding essentially all the candidate edges to G. So now the goal is, only by adding few edges, order of k of them, to G, is it possible to improve the algebraic connectivity to be close to the best with respect to the candidate edges. And to solve this problem, we look at a stronger notion, which is that of subgraph sparsifier. Say that the weighted subgraph W tilde of W with order of k edges is a subgraph sparsifier of G if these two Laplacians are similar to each other. So when adding W tilde to G has the same effect as adding W to G. And again, you should view this W tilde as just the subgraph corresponding to these good edges, these targeted edges F. And okay, why is this stronger? This notion stronger? It turns out that because we're considering the two Laplacians to be similar, not just the second eigenvalue, but all the eigenvalues of the two Laplacians will be the same. The nice thing about the subgraph sparsification problem is that it has a very nice linear algebraic equivalent formulation. For that, I need to introduce one more piece of notation. So for any edge uv and an arbitrary orientation, let's say going from u to v, we define the vector be to be just the n-dimensional vector who has 1 in position corresponding to u and minus 1 in position corresponding to v, and 0 everywhere else. And it turns out that the Laplacian matrix LG plus W can be written as a sum of rank 1 matrices, where the rank 1 matrices are B transposed, and the summation goes over G and W. And the problem of computing a subgraph sparsifier W tilde essentially reduces to the problem of sparsifying the second summation, the one corresponding to W, with only order of k non-zero scalars, such that the resulting matrix is similar to the initial one that we started with. There's a very simple reduction saying that actually we don't need to consider Laplacian matrices. It suffices to view them as the identity, and the orange summation corresponds to some matrix X. And the new problem that we're trying to solve is, given the matrix X and m vectors Vi such that X plus the sum of rank 1 matrices Vi transpose is the identity, we want to find scalars Si, order of k of them non-zero, such that the sparsified matrix is similar to the identity. So again, this is the problem that we are trying to solve. In 2010, Kola et al. Gave a deterministic algorithm for finding these scalars Si, theta of k of them non-zero. And their algorithm essentially proceeds in rounds. Initially, we start with just the matrix X, and iteratively in each iteration I, we add one rank 1 matrix, Vi transpose, and an associated scalar Si to do the update. And after 8k rounds, we end up with this sparsified matrix. Now, in order to find the appropriate rank 1 matrix in iteration I and the associated scalar, Kola et al. Introduced a fixed projection PS to essentially measure the contribution of each of the possible rank 1 matrix that we can add. And based on this, they decide which one to choose in iteration I. And the careful analysis shows that, as I said, after 8k rounds, this sparsified matrix is close to the identity up to some parameter kappa, which depends on the initial matrix X and the number of iterations k. And our contribution is inspired by the work of Li and Sun in 2017. We give a faster randomized algorithm for computing the final matrix A8k. Our algorithm combines several of these iterations that I've mentioned, groups them into phases, and in each phase we sample multiple vectors Vi with a carefully crafted probability P of Vi, and we add the corresponding rank 1 matrices. Now, from the analysis point of view, in order to compute these probabilities Pi, it would be convenient to use the projection matrix PS to measure the contribution of each Vi. However, using the exact projection PS is not great because computing PS takes a very, very long time. This is a fixed projection. So what we're doing is we are replacing this projection PS with an approximate projection PV, which is fast to compute and which will imply a significant improvement over running time. And obtaining this projection PV comes from the work of Alan Ju and Lee in 2017 from an independent direction. And we show that the probabilities defined with respect to this PV are sufficient for our purpose. And our algorithm runs in time m o tilde of mk squared n to the epsilon. Again, if you take k to be small, let's say log n, we see that the running time is almost linear, which is a significant improvement over the running time provided by Koller et al. Okay, now it's time to do a wrap-up and give a summary of what I discussed so far. So we studied the problem of augmenting the algebraic connectivity of graphs, lambda 2. To that end, we defined the notion of k-gamma augmentable. We give a randomized algorithm that finds a desired set of candidate edges F of size order of k for the regime when this gamma is at least delta times n to the minus epsilon. And our algorithm is based on two technical results, a fast SDP solver and fast algorithm for subgraph sparsification, both of them of independent interest, independent from this problem, and we hope that these two tools will have further applications. And I would like to conclude by posing an open question. So you see that we've given an algorithm that runs in almost linear time for small values of k. And the question would be whether it is possible to bring this running time down to just nearly linear m for the problem of k-gamma augmentability. And I will stop here. Thank you.